In this video, we solve this differential equation. So first we're going to let y equal x to the lambda power, and we're going to substitute that into the original differential equation. So in order to take the derivative, we're going to use the power rule. So bringing down the exponent, subtracting by 1. So for the second derivative, we have to bring down two exponents, and then subtract the exponent by 2. And now we can simplify this. X squared times x to the lambda minus 2 becomes x to the lambda. X times x to the lambda minus 1 is x to the lambda. So notice that each of these terms has a factor of x to the lambda. So we can factor that out. And inside the bracket, we have lambda times lambda minus 1 plus lambda plus 9. So this simplifies. We have lambda squared over here minus lambda plus 9. The lambdas will cancel, and we're left with lambda squared plus 9. So here we want to set each of the factors equal to 0. But notice x to the lambda does not equal 0 when x does not equal 0. So I don't care what lambda is, this will never equal 0 as long as x is not 0. So we're going to ignore that, and we'll let lambda squared plus 9 equal to 0. And we get lambda squared equals negative 9, which lambda is plus or minus 3i. So for the root that lambda equals 3i, that's going to give us solution c1 times x to 3i, because recall we said y was equal to x times lambda, x to the lambda power. So lambda is just the root. And then for lambda equals negative 3i, we get c2 times x to the negative 3i. So now we bring it all together, and this is our solution. But we can use Euler's identity and simplify this further. So Euler's identity says e to the a plus bi is e to the a times cosine b plus I times e to the a sine b. Or if you want, you can factor out the e to the a. You're left with cosine b plus I sine b. So x to 3i. First we have to rewrite it as e to something ln of x. Because the idea is you need to have e to a power, basically, in order to use this identity. So in general, x equals e to lambda x. So that's what I have here. And for x to 3i, we would have e to the ln of x to 3i, but this exponent will come out in front, and you'll have e to the 3i times lambda x. So I skipped a couple steps here. So that's what we have, and this one should be a negative. Okay, so we just plug it in. Don't forget the C1. So I didn't do it for this step right here, but technically there was a C1 originally and a C2. And then we have x to 3i plus c2 x to negative 3i. So that's just c1 e to the 0 times cosine 3 ln x, because if you ignore the I, 3 ln of x will be the b over here, and then the negative 3 ln of x is going to be the b for the other one. And there's no a here. A is going to be 0 in both cases. So that's why I have the e to the 0 power. So what goes inside is just b, which is 3 ln of x, and negative 3 ln of x. Now, this is just 1. And then cosine of negative, in general, cosine negative x is just cosine of x. So this is positive. And then sine of negative x is negative sine x. So this is positive, and it comes out as a negative. So we have cosine 3 ln of x in both of these with coefficients c1 and c2. And then we have sine 3 ln of x over here with coefficient c1 minus c2. And then don't forget the I in front. So we can simplify this. This is a constant, right? When you add two constants, you get a constant. So I just let it be C1. And then common mistake here is to think that I is not a constant. So I is indeed a constant. So I'm going to call this whole expression C2. And so this becomes my solution.